Можно начинать.
Well, let's start. First, I would like to recall that we have the following very important construction. If we have an oriented vector bundle over smooth manifold, then we have got two mutually inverse isomorphisms. We can consider homology of M, the rank cohomology of M, and we can consider the rank homology of E of the total space with compact vertical support. We have discussed what it is, compact vertical support, and we have this shift of dimension by
Можно коробочку с минутами? Так тоже сойдет.
Here we have shift by the dimension of the bundle, and here stays the rank homology of E. And we have two isomorphisms in this direction. This is multiplication by Thom class, and which is an element of nth group of and in that direction, this is integration along the fiber. They are mutually inverse and they are isomorphisms. This is what we have already discussed. Today, I would like the first thing I would like to discuss today is the relationship of this important construction with Poincare duality. We have discussed already Poincare duality from the following point of view. We have discussed that K, the rank homology of M. Yes, what do we need to have this isomorphism? We need that the bundle is oriented. The bundle. To have Poincare duality, we need to have that manifold is oriented. Then we have a non-degenerate pairing. Non-degenerate, this is dimension of the manifold. Non-degenerate bilinear pairing, so this, where in one place I need to take compact support. Let M be of finite type, as usual. I don't want to discuss general situation. If M oriented of finite type, then we have such Poincare duality. This is nice, but not nice enough. The fact is that let us for a moment discuss when we deal with usual singular homology. I don't want to speak much about them, but for those of you who studied singular homology in some, there are several ways to study it, but what is Poincare duality in singular homology? For a moment, let M be compact without boundary. I just don't want to consider general case, just some idea. Well, in singular homology, Poincare duality is isomorphism between homology and cohomology of corresponding dimensions. So we have singular homology of M, and we have chain, and this pairing is non-degenerate pairing between kth singular homology and kth singular cohomology. Here we have, if we have coefficients in some ring, then we get to R here, where R is an arbitrary ring, commutative ring. Look, what do we see? We see that once we have such an isomorphism, we immediately obtain a pairing like that. I say that now we restrict ourselves to a compact manifold, so this doesn't matter. And once we have an isomorphism between kth homology and m minus kth cohomology, we immediately, this pairing turns out to be that pairing. So Poincare duality in this form, in the form of isomorphism, immediately provides Poincare duality in the form of pairing. Well, and actually over a field, if R is a field, then this pairing is always non-degenerate. And actually, these are equivalent points of view. If we have a field, then to say that this is an isomorphism is the same as to say that the corresponding pairing is non-degenerate. But if R is not a field, then say the most interesting case is R equal to Z. Then of course this is not so direct. We have here some torsion. We can have here some torsion. The pairing is non-degenerate and unimodular on free paths of groups, but concerning torsion, we lose some information. And Poincare duality in this form is stronger than Poincare duality in that form. So again, once we have this isomorphism, it follows that on free path of homology groups we have non-degenerate pairing, but there is no opposite implication. This is strictly stronger over that. Of course, in the RAM setting, we live over a field, namely over the field of real numbers. But still, it is useful and it is very convenient that actually it is really an important thing to have some analog of Poincare duality in this form of isomorphism. Yes? But the problem is that we do not have any homology in the DRAM setting. We have cohomology, but we do not have homology. So we still need to use singular homology. But in fact, what is singular homology? Just by definition, we need to consider kth chain group. I just would like to recall that this chain group is, by definition, linear combination of singular simplices. Well, singular simplices are such mappings, continuous mappings of standard simplex to X. This is standard definition. I don't want to discuss it in details. Just I would like to say some one thing on the level of some ideological thing, and not precisely. When people define singular homology, they usually say, okay, we have such singular simplices, and then we take formal combinations with coefficients in the ring, and let us for simplicity take that here. Then just with incongruent coefficients. Yes, and then we define boundary operator and so on. And actually a homology class is represented by a formal linear combination of such singular syntheses. It is a very convenient geometric point of view here. Instead of mapping each synthesis individually to X and then taking a linear combination there, it is often convenient to glue a cycle from synthesis first and then to map the whole cycle to X. This is just a viewpoint. This doesn't change anything, but this is very convenient viewpoint. And what I'm going to, I would like to lead you to the following idea that when we are trying to study differential topology, we are trying to study only topology of smooth manifold. We don't want to work with arbitrary topological space in this course. And in smooth manifolds, there are very important cycles. There are very important homology classes which come from smooth submanifolds. These are still singular homology classes. They live in singular homology, but these are not all homology classes. These are some special homology classes. So now, if we have a submanifold, for simplicity, let everything be oriented. So we have oriented manifold and oriented submanifold. In M, first let everything be compact without boundary. Compact without boundary. Then we immediately obtain the fundamental class of this submanifold, which lives in S-dimensional singular homology of M. And such classes will be very important for us, and such classes will be very important for us. And actually, to deal with these classes, we even do not need singular homology, more or less. It is sufficient to work with only these. But if you know something about singular homology, then you can take a triangulation of S, and you obtain its fundamental class. And it is independent on triangulation. We get a well-defined homology class in this singular homology.
We assume that our manifold is oriented here.
Yeah. I say everything is oriented. There are actually in some. To define this, we need only orientability of S. But let's assume that everything is oriented. There are some versions where some of them are not oriented.
No, I can replace the 2.
Yeah. Over the 2, yes, it works always. But let us now consider that everything is oriented.
Можете повторить, что вы сказали, что вот про фундаментальный класс, что можно триангулировать, и можно...
Yes, if we actually want to obtain this fundamental class as an element of singular homology, then we need to triangulate S.
А вот вы перед этим сказали, что можно не триангулировать и что другое.
To work with this class, to think about actually what we actually need. We need a version of such pairing where here we have Dirac homology. To pair Dirac homology with such homology classes, we do not need to triangulate it, we do not need to do anything, we just need to integrate. So this is an important idea. So we even do not need to know what is singular homology to work with this particular homology class. But just one important thing, that not all homology classes here come from submanifold. This is very important. So not all homology classes in singular homology can be represented by submanifolds. This is not an easy theorem, and I'm not going to prove it, but just it is important to understand that not any class can be described in this way. Actually, this is a rather deep theory. It is called problem on realization of cycles. It has two versions. We can try to realize cycles by submanifolds or by continuous images of manifolds. In both cases, not all homology classes can be realized, and there are deep topological abstractions, but this is out of our scope. Of course, once we consider not all homology classes, but only those which are represented by submanifolds, we cannot hope to obtain an isomorphism, any kind of isomorphism. But what is important for us important is correspondence in one direction. We would like to construct for a submanifold, to a submanifold, we would like to assign the dual homology class. This is actually an important construction, and this is what I'm going to tell about. Is it okay to use this?
No.
No, it's very good. Okay. So now the situation is as follows. Actually, one more comment. For singular homology, we also have, usually singular homology is, we allow only finite combinations of simplices, and then it's usual singular homology. We also may allow locally finite combinations of simplices. This means that the sum, this formal sum, is infinite, but for each point in X, there is a neighborhood such that only finitely many of simplices meet this neighborhood. Only finitely many of singular simplices, their images intersect with this neighborhood. This leads with some locally finite homology, which allows to obtain similar things for non-compact manifolds S. So I don't want to speak about the singular homology in this variant, but I would like to say that, okay, we will have dual homology classes not only for compact submanifolds, but also for non-compact submanifolds. But actually, we need the following condition. So, generally, we have the following situation. Assume that we have a submanifold S M, and what do we want? We would like that S in M is a closed subset. Closed complement is open. Yes, so topologically closed. So we allow S to be non-compact, but what we do not allow is things like that. Say we can consider submanifold which behaves like such spiral, which approaches a circle. So say, assume our M is a plane, M is R2, and S is such spiral which approaches this circle infinitely many times. This is not allowed. This S is not closed in M. So in this case, there will be no good Poincare dual clause. So our condition, we do not require S to be compact, but we do require that S is topologically closed. Of course, if S is compact, then its image is compact and of course closed. So for compact submanifolds, no problems. And in this case, we can give the following definition. So yes, and we still assume that both S and M are created. So if we have such a situation, then we can give the following definition. Cohomology class. Cohomology. Yes, and again, for simplicity, I don't want to deal with some infinite phenomena, so all of them are finite type. Actually, we need only that M is finite type. But actually, it's better to assume both are finite type and to avoid any difficulties. In all interesting examples, it is like that. So a cohomology class, let us denote it at the S, which belongs to M minus S of M minus M's de Rham cohomology. Starting from this point, we again return to de Rham cohomology. We do not think about singular homology. M minus S de Rham cohomology of M is called the Poincare dual of S. Is said to be Poincare dual to S if we have the following. Yes. If we have the following situation. Assume that I first write the formula and then explain. The formula is like that. Okay, in all this stuff, in all this topic, it was actually convenient to sometimes not distinguish in notation between a form and a cohomology class. So I'm sorry, I write down integral of a form, but I say that it is a cohomology class. I mean that we need to take a form which represents a cohomology class and then integrate. And this a homology class. This equality must be true for any. Again, I write a homology class, but I mean that we can take a form for any S-dimensional form with compact support on S. Look. Sorry. On M. look, if we have got a compactly supported form on M, closed form, then we can do two things. We can either integrate it over S, to be precise, we restrict our form to S and then integrate. Since it's compactly supported, it is well defined. Yes? It is important that S is closed here, if we consider this thing. Once again, if we consider this nasty situation, then look, assume that we have a form, a compactly supported form on M. Its support is like that. We intersect it with S and we get not compactly supported form, and the integral may be not well defined. But if it is topologically closed, then such phenomena never occur. Well, but on the other hand, we can first multiply this omega by the class at S, and then integrate over the whole M. Omega is compactly supported homology class, eta is an arbitrary homology class, multiplication is compactly supported, so we can integrate. Of course, if we change omega inside its homology class or eta S inside the homology class, the integrals do not change. Since by Stokes formula, the integral of a closed form is always 0. Okay, so this is a definition. First of all, why this is a good definition? The matter is exactly like that. That here we have pairing between homology and cohomology. We take cohomology of N and we pair it off with homology. We integrate by a side. Well, along a side. And here we have this kind of pairing. So this graduality is what the thing which relates this to that. So this is an intuitive explanation why this is a correct definition. Why this is a good definition. The definition cannot be correct or incorrect. Can be good or not proper. Well, what is important? And important is that Poincare duality, this dual homology class always exists and is unique. This is an easy proposition. Poincare dual homology class exists and is unique. Why?
No, it is combination of of this pairing and this pairing. No, if we assume that
yes, actually we do not need
pairing is non-degenerate.
If we assume that it is non-degenerate, if we say that singular homology is isomorphic to the regular homology with R coefficient, but actually we do not need all this. We need only one thing. We only need that this pairing is non-degenerate. Look, what we know. If we look on the left-hand side of this, yes, on the left-hand side of this, if we take omega and map any omega in here to its integral over S, then this is a linear map from this compactly supported homology to R. Yes?
Yeah.
And it's linear. And by Poincare duality, we know that this is a finite dimensional space, since we have assumed that M is of finite type. And we know that the dual vector space is M minus S cohomology of M. And moreover, this isomorphism is provided by such pair. We have proved this. And of course, this immediately implies that our class at the S exists and is unique. Well, so this proposition is rather easy. Okay, this definition has the following analog. Actually, if a submanifold S is compact, then we can say more. Up to on this blackboard, S is not assumed to be compact, but sometimes it is important that if S is compact, then we can say some more. Namely, so assume additionally that S is compact. Then we can define the dual cohomology class not in usual Dirac cohomology, but in completely supported Dirac cohomology. So again, definition: a class, let it be at the S prime in the Dirac cohomology of M, but now completely supported Dirac cohomology. The same is said to be the Poincare dual of M, the same as here. If the same formula, yes, here it for any omega, of course. I forget, I said it, but I forget to write down. The same formula, but now it is true for any omega. For arbitrary closed form on M. We do not need to take completely supported here. First of all, we can always integrate over compact submanifold, arbitrary form. And here we have compact support because eta S prime is compactly supported. Yes? In the same way, completely similar, I even not going to write it once more, but such Poincare duality class also always exists and is unique. Just in the same way, just to we have known the general pairing between usual Dirac cohomology and completely supported, and we can put this completely supported sign on any of the two parts. So if S is compact, then we can define dual cohomology class in this sense and in that sense. This is more important. Why? Once we have this, we can always forget about it. It's compact support and get this, but not vice versa. So we always have such a map. This is just general thing. For any M, for any dimension, we always have such a natural map. And this at the S prime, which lives here, comes to at the S, which lives there. So we lose some information when we go from here to here. So for compact submanifolds, this one is more important, but it is also important that this one works not only for compact one. Okay, so we have such Poincare duality classes, but what is more important for us, this is only existence, but what is more important, and a very important thing is that Poincare duality classes are very closely related with some isomorphism. And let us discuss how they are related. Yes, to discuss this, we need for a moment to forget about homology and cohomology and to discuss what is the tubular neighborhood of a manifold. If we have a manifold, then we have its tubular neighborhood. Just naively. Suppose that we have a submanifold S in some manifold M. Then we have something like tubular neighborhood, some tube around S, but and also we have another important thing. We have normal bundle for S in M. Normal bundle. What is a normal bundle? A normal bundle is a complement bundle. We can take tangent bundle to M, but then restrict it to S. Then it is a bundle, a vector bundle over S. And here we have tangent bundle to S. Well, and we can choose a complement bundle. The most convenient, a complement bundle up to isomorphism is independent on which particular complement we choose. This is a standard fact of vector bundles. But the most convenient way to choose it is to endow M with the remaining metric. And then we just can choose orthogonal complement to the tangent space. So we get this normal bundle. Let us denote it to N over S. So this is just normal vector bundle of dimension M minus S, where M is dimension of M and S is dimension of S. What is a tubular neighborhood? Actually, a tubular neighborhood is a way to embed this normal bundle to M. So, by definition, a tubular neighborhood, there are many different tubular neighborhoods, of course. A tubular neighborhood of S is a way to define an embedding from M to M, well, such that it is identical on the zero section. In this M, we have zero section. Zero section is S. Yes? And we would like that here we have this our S is a manifold of M. So we would like to have an embedding of M to M. M is a manifold of the same dimension as M. So this is just an embedded onto an open subset of M, onto this tube. And this embedding should be compatible with our embedding of S to M on the zero section. So if we have a zero section here, then the diagram must be commutative. This is a tubular neighborhood of S. How to construct a tubular neighborhood? There is a more or less standard construction using geodesics. So if we endow M with the remaining metric, then what we have? We have such exponential map. If we have actually this is general situation in differential geometry, even without any submanifold. If you have a point x in M, and then we have got an exponential map from tangent bundle to M at x, from tangent space, yes, to M. How it is defined? By definition, if we would like to compute the exponent of the exponential of vector c, then we need to start a geodesic. We can consider a geodesic with gamma, which starts at x with speed c. So we start from c, and then we have a unique geodesic with this data, and then we take gamma of 1. I just recall that geodesics can be written by explicit differential equations. I would like just to recall it. Here in coordinates, it's like that. This is differential equation where gamma ijk is just written.
Levi-Civita.
Yes. It's a standard Levi-Civita connection. Sorry. The formula are too long to write them in such small piece. So equation is like that. It's second order differential equation. And where this gamma ijk it is not actually important for us what is an explicit form for this, but it is important if we would like to compute geodesics explicitly, but just at the moment we only need that there are such expressions that they are expressed smoothly. There are expressions of such kind. So if we know Riemannian metric, it's the infinity. We just compute these are just some locally. These are some smooth functions on our manifold, and we have precise equations, differential equations, with smooth functions here. So their solutions exist, are unique, and depend smoothly on initial data and so on. Well, and this, what can we do in our situation? In our situation, we can use this. So this what we know about this exponential map. Which properties do we know? First of all, it is smooth, yes, and we also know an important thing. So we need only two things. First of all, smooth, and second, we know what is the differential of the exponential map at 0. Yes? The differential exponential map at point 0, we have point 0, is just identity. The tangent space to the vector space is vector space itself. So, of course, exponential map takes 0 vector to the point differential just identity. We need only these two things. And what we can do with tubular neighborhood then, we can do the following. We can say that exponential map provides the following map. The map from, I denote by n the total space of the normal variable. Yes? So we get such a map from n to m, which behaves like that, which takes every what is a point in n? A point in n is a pair x and xi, where x is a point of S and xi is a vector orthogonal to S. Yes? Orthogonal to S. And we these two exponents of S. So what we see, this is smooth. And again, it's we have the same process. It's differential at so this is smooth, and it's differential at points. We have points like that, arbitrary point C here, arbitrary point X, and zeros vector. Its differential here is identity.
Sorry, I'm confused.
Well,
how can we apply? I'm confused here. How can we apply exponential to Kasi? Because Kasi is something orthogonal to the tangent space. Am I right?
but we apply exponential in M, not in S.
We can restrict.
Yeah, we apply it in
okay,
M.
okay, yes.
Yeah, of course it is very important that we have this ambient manifold M.
Right.
We apply it into M. So the idea is that we just start a geodesic in M, not in S, in the orthogonal direction to S. And we look at time one. This is not the required method. We would like to have an embedded, but we have only some degenerate. But what is important? It is important that the differential is non-degenerate on the zeroth section, and hence this is locally an embedded. Just by implicit function theorem, this is locally an embedded. We can reverse this map. This is some auxiliary map. Let us denote it by, well, it comes from exponent, so let it be. Yes? This is some auxiliary map, and we know only that we can locally reverse it near S. Yes?
Мы считаем, что S замкнуто?
Yes, this is our, and if S were compact, then just how to repair, how to fix this problem, how to obtain an embedded. If S were compact, then we just have that locally near S means that there is one particular epsilon such that on vectors of which are smaller than epsilon, it is always an embedded. So if S were compact, then we just would write, how to write I. So this embedded I on pair XC, we can just how to do this? We can, for instance, we can rescale C. I would like to write down some how to. We need to rescale C using some monotonical function which is bounded by epsilon. So this is something like that. well. Instead of arctangents, we can take any monotonical function. Just we need that it is smooth, monotonical, and bounded. This leads to the fact that vectors xi become, we apply this E only to small vectors xi, and this works rather well. If S is not compact, we need to put here some function E of x, which is strictly positive, but depends on a point. So for actually, I just would like to say that all details here can be filled. It is a good exercise. Do it in all details. Fix all details in this proof. But for me, it is more or less important just to know that there is such a neighborhood which behaves like a normal bundle. So we can always assume that normal bundle, the total space of normal bundle, is embedded into M. And then what we can do? Then the claim is as follows. Look. Again, the same situation. We have S. It is a submanifold of M, closed, both oriented. But now we have managed to construct this tubular neighborhood. Yes. What do we have? This is a vector bundle, and it has there is a some isomorphism, and we have, in particular, we have here a some class. Some class of normal bundle. Yes. To S in M. It lives in cohomology with compact vertical support of dimension M minus S. Here we have dimension M and here S, and of M, of the total space of this normal bundle. If you have got a form which is not compactly supported along S, but is compactly supported in this vertical direction, yes, then you still have a well-defined. I would like to say that this inclusion defines a well-defined push forward from compact vertically supported cohomology of N to usual Durand cohomology of M. Well, and proposition is that this push forward takes the sum class of N to the class which is Poincare dual to submanifold S. So this is an important proposition. I will prove it in a few seconds. Just why this is important. This is important since it's well. First of all, some class is useful thing, and some isomorphism is useful thing. But also, a meaning of this proposition is that from this general situation, from this general Poincare duality, we only know that such class N exists. But from this, we immediately see that this class can be supported in an arbitrarily small neighborhood of S. it is a useful understanding that this class is some head form near S. We have S and we have something like that around S, and it can be chosen 0. Of course, this is by no means true that any form in this cohomology class is supported near S. Of course, this cohomology class contains a lot of forms which are not supported near S, but it also contains a form which is supported near S. Well, for instance, this immediately implies the following corollary. That if we have two submanifolds which do not intersect, then the corresponding cohomology class, the product of them is 0. So assume that we have two submanifolds of any dimensions, such that they are disjoint from each other. Then the product, the usual cohomology product of Poincare dual classes is 0. This is just immediate. This one is supported near R, this one is supported near S. So if R and S are disjoint, then the product of corresponding forms is 0 everywhere. So this is an immediate corollary of that proposition. Now let us prove this. Actually, this is a very easy proposition. We have already proved it, to be honest. We haven't formulated it, but we have already proved it. Look, if you have an arbitrary, compactly supported form, yes, we need to prove. So we would like to prove that this homology class, yes, has that property. Well, so we would like to consider the integral over M. Well, let us take an arbitrary omega, yes, and we would like to consider an integral over M, omega times E star of phi n over M. Well, okay, what can we say? We can look, this form is 0 of the tubular neighborhood. So I can replace here integral over M by integral over tubular neighborhood. And moreover, I can take the pullback of all these forms to N and integrate there. Yes? So I can write down like that, I would like to have integral over N, yes, of the pullback of omega yes, but well, what can we?
We can identify, I think, with cohomology of N. Cohomology of N with cohomology of S. Hence why pullback of omega it is something from S, not like this. And use Tom.
One delicate thing is that this is not compactly supported anymore. The compact support of omega can be like that. This is not a compactly supported thing. But what can we do? We can apply well, one moment. It should be very easy. I'm sorry. Actually, if this were compactly supported, then it would be just what we see here. We actually see this is exactly the claim that Thom isomorphism multiplication by Thom class is a reverse to integration along fiber. But one moment, I'm sorry for. This is so obvious that I even didn't write down it in my preparation.
Why do we if почему все хорошо, если и со звездочкой омега компактный носитель?
What we know that homology with compact vertical support of we do not need any. Let us just prove it in general situation. This is very easy. One moment. We just have look here. We do not have
ну нам же не нужно, чтобы вот этот pullback был в принципе компактный носитель. Нам нужно только, чтобы в слоях, по-моему...
Нет, как раз в слоях. Вот это как раз в слоях не компактный. Если он вот такой, как раз...
Но мы же его...
Как раз в слоях он не компактный. Он как раз в горизонтальном направлении компактный. Здесь все наоборот. This one is compact horizontal support. It is compact in that direction, but is not compactly supported in vertical direction. But phi n is compactly supported in vertical direction. It is not. And so together they are compactly supported. Well, actually, this is just let us say that this is a general fact about Thom class. We actually let us denote it by theta. This is an arbitrary theta on. So what is the situation? The situation is like that we have an integral over n of some form theta, closed form, multiplied by some form, yes. And for this theta, we know that it is. It has compact support in horizontal direction, but not in vertical one. What can we say in this situation? Here we only need that n is a vector bundle. What can we say? We can first one second.
Извините, ну, мы как бы знаем, что эта штука, она компактная на слоях. Потом она, значит, вот эта вместе форма, она уже пришла из S, ну, из нашего подмногообразия. То есть она равна, грубо говоря, бета на вот
which form comes from it? Which form comes from? Okay, okay.
we know that totally this form is compact on fibers.
Yes.
Hence why it comes from some closed form on our submanifold with Froh-Thom isomorphism. So it is equal beta wedge product
What is
class.
beta?
No, beta is something that come from submanifold S.
I think I have another explanation.
Yeah.
У нас была формула проекции,
Да, вот.
что у нас, если произвольно есть форма на S, мы берем ее pullback относительно проекции в векторном выстроении, там будет как раз, что ее wedge продукт с омега, которая compact vertical support в E, ну что интегрируем по слоям от этого, это wedge продукт на интегрирование от омега.
Yes.
И мы можем θ заменить на...
First we can replace theta by, we can say that theta is cohomological to some element in, to some form of the form the star of psi.
Мы не можем написать π со звездочкой от θ ограничено S?
Yeah, very good. Yes, that's the first step. And this is something like homotopy invariance. This is somewhat non-standard homotopy invariance, but still, well, let us. This is an exercise to prove this precisely, but it is just standard homotopy. After that, let us. So we can rewrite this. Let us denote it by psi, just to avoid, and we can rewrite this by like that. Yeah. Now we can say that when we take integral over n, we can first integrate by fibers and then integrate by along S. And we have already discussed it, that always when we integrate along the total space, we can always integrate by fibers and then integrate by S, by the base. So we can rewrite it as integration by base of integration by fibers of this form inside the start side times phi n. Yes? Now we can use projection formula. So we get integration of S of what? Of psi times p star phi n. But this is a definition, one of the definitions of Thom class, that this is just one. So we get integral of S of psi. And that's exactly what we need. The matter is that our psi is the same as omega. We have come from omega to theta, from theta to psi, but all of them coincide on S. So this is the same as integral of omega, and that finishes the proof of proposition. And completely in the same way, if S is compact, then in fact, if S is compact in addition, then this compact vertical supported homology come to compact supported homology of M? Well, if S is compact, then if we have compact vertical homology of M, then the support of the resultant form is compact in M. So if S is compact, then instead of this one, we can write down this one, and in their proposition, which is proved directly as this one, is that in this situation, I star of N is this more delicate Poincare dual of S, which is completely supported. Actually, this one was slightly easy, and I forget. I would like to consider this case first, and then it will be much easier, and then say to you that it is an exercise to do this in general situation. but
is there a typo?
Well,
the push forward should start from compact homology of N.
Of N, yeah. I'm sorry.
And in this case, we are starting from compact homology, not compact vertical.
In this case, there is no difference between them. So both are true. When the base is compact, then compact vertical and compact is just the same. Well, so we have these two important propositions. We have this relationship between Thom isomorphism and duality. Well, I think that it's time to finish now and have a break. Let us today maybe we proceed with the lecture, some part of the second part. The matter is I would like to come to some important things that maybe we have. But now let us have a break for 10 minutes.
А можно вопрос?
Да, конечно.
А как в случае топологического многообразия определяется фундаментальный класс?
По Майеру Виталиса. Он вот в этих вот локально, то есть это не так просто, это не так, что триангуляции нету. Вот, значит, идея такая, что если мы берем локально топологии, когомологии с локально конечными носителями, то фундаментальный класс существует не только для замкнутого, не нужна компактность. Он существует для произвольного. Вот. А дальше по Майеру Виторису мы его склеиваем, он существует из того, что он существует для одной кусочка, и для второго кусочка, и для их пересечения, мы выводим, что он существует.
А потом говорим, что локально конечный на компактном это просто обычно.
А потом, да, приходим к компактному, и там нам не важно. И это, знаете, если интересно, очень хорошо написано, есть такая книжка Милнер-Сташев «Характеристические классы», и у нее есть, там называется приложение А. Вот. И это такая вот очень кратко про гомологии и когомологии, очень хорошо. То есть там ничего про характеристические классы не надо знать, чтобы прочитать это приложение. Оно как раз чисто такие основы. И вот там это и двойственность Пуанкаре тоже.
Ну там вот как раз, по-моему, они через Майера Виториса.
Да, только, по-моему, по-другому и не умеет никто для произвольных топологических многообразий. Вот, по-моему, более-менее единственный способ.
Ну да.
А я вот читал эту книгу, но только первую половину примерно. Там выделяются вот классы Штифля-Витни с помощью операций когомологических.
Да.
Чтобы через Стинреда.
Да.
А вот можете объяснить, что такое вот эти квадраты Стинреда?
Это стабильная операция.
Значит, смотрите,
за 5 минут это тяжело. Вот. Значит, есть несколько возможных пониманий. Есть понимание такое, что что такое вообще космологическая операция? Это на самом деле, вот, давайте с коэффициентами за 2, да? Это на самом деле класс когомологий пространства К за 2n, пространство Берг-Маклейна. Почему?
У Йен нет вот это.
Я предпочитаю без страшных слов, банально, если у вас есть класс когомологий, то это то же самое, что отображение в К за 2n. Есть такой... Можно скинуть ручку? Да. Есть такая общая вещь. Когомология икса с коэффициентами, на самом деле, в любой абелевой группе, nt, да? Это находится во взаимном соответствии с гомотопическими классами отображений вот этого сюда. Вот. Это общий как бы факт, но и он не очень сложный. Вот. Ну, соответственно, допустим, если у вас есть класс гомологий, да? Ну, вы прям можете считать, что это то же самое, что отображение этого в КАЯ. Это просто вот удобно. Ну, с точностью гомотопии, но здесь у вас есть, как бы, смотрите, как устроены гомологии. Давайте теперь поставим за 2 везде. Ну, хотя можно ставить разные вещи. Да? Как устроены когомологии К за 2n? Ну, мы точно знаем, что они начинаются с размерности n, да? Ну, 0 не интересно, да? До размерности n ничего нету, потому что оно односвязанное, там, понятно, да? Гомотопические группы 0. Ну, как, что такое?
Мы смотрим на отображение, получается.
Подождите, я не хочу сейчас смотреть на отображение, я хочу посмотреть на само это пространство, на его гомологии. Что мы можем про них сказать? Их нету до размерности n по теореме Гуревича, а в размерности n мы наблюдаем за 2. Да? А вот дальше мы наблюдаем что-то. Да? Если мы знаем какой-нибудь класс здесь, там, не знаю, в размерности q, s, да? Давайте зафиксируем этот класс, то вы всегда можете сопоставить, вот взять а звездочка от s. И вы получаете корректный То есть, как бы, смотрите, что теперь получается. Вы по любому классу, давайте s зафиксируем, а будем брать разные. По любому классу когомологии умеете вычислять класс когомологии большей размерности. Ну, вот. Значит, а дальше вопрос, это конкретное пространство, у него можно конкретно посчитать когомологии. Люди это посчитали и получили явное описание, как бы, то есть, на самом деле еще следующий шаг, что нам интересны стабильные когомологии. Значит, вот эти когомологии, у них как бы первый кусок, если вы переходите от К за 2n плюс 1, то он как бы сдвигается на 1, там вдали что-то меняется, и это вот насколько вдали, то есть по-хорошему нужны когомологии спектра.
Слышал,
да. Это вот, да, это как бы, вот. Это прямой, в общем, не прямой, в общем, это предел этих самых когомологий К за 2n сдвинутых. Вот. Дальше это вопрос вычисления. Это одна точка зрения на то, что такое гомологическая операция. Вторая точка зрения, на самом деле, их можно добыть есть просто явная конструкция, можно как бы их добыть из так называемых вариантов когомологий. Можно взять прямое произведение, прямое произведение нескольких иксов, да, подействовать на них циклической группой и как бы слушайте, это я не объясню за 5 минут. Вот. Но в общем, на самом деле правильная точка зрения, что вот квадраты Стинрода это результат вычисления вот этой вот алгебры. Ну, по модулю P вот этой, то есть, как бы, вот, в принципе правильно, что просто любой класс когомологии здесь задает когомологическую операцию, а то, что они именно такие, это вот просто люди взяли и посчитали. Вот. Ну а какие они именно, это надо как бы понятно. Вот.
Я еще слышал, что они образуют алгебру Хоффа.
Они образуют алгебру Хоффа. Значит,
они...
смотрите, да, понятно, почему они образуют алгебру, потому что их можно композицию брать. Ну, можно одну применять, а другую. Как раз, если они стабильные, то их можно применять к классам любой размерности, и поэтому их можно композиции брать. А коалгебру они образуют, потому что они действуют на алгебре. Их можно применять к произведению классов. И это расписывается через применение к одному и к другому. Это дает структуру коалгебры. Ну и вместе действительно. Ну это вот есть Стинрод Эпстейн, очень хорошая книжка. Введение в когомологические операции.
Я вот у Фукса читал, ну там не надо, наверное, это как-то старый взгляд на это все.
Файминг Фукс?
Ну да.
Там другой взгляд, да, чем в Стинроде и Эпстейне. Вот. Ну, оба хорошие на самом деле. Вот. Сейчас я.
Спасибо.
Ну, у тебя там, смотри, где-то она из тождества картана. У тебя то, что на Хопфу, это тождество картана, по сути.
Которая магическая формула картана?
Нет, ну у тебя есть, что типа у тебя, если ты применишь полный квадрат Стинрода к альфа бета, ну, к произведению, то есть он что, произвести их. Ну, по отдельности применить и произвести. Вот. Но это, вот это плюс-минус и говорит, как выглядит. Ну, то есть, там будет, типа, выглядеть что-то типа, ну, по логике вот так. Там как-то. Ну, там другое дело проверить, что это так. Ну, там будет вот так как-то. Вот. Ну, типа, у тебя идея, что, типа, зачем тебе нужно Хопфулу? Структура, это, ну, чтобы, если у тебя есть какие-то два модуля, чтобы на их тензорно как-то действовать. Ну вот, а у тебя вот тождество картана уже говорит, что мы как-то умеем действовать. Ну, это просто переформулировка одного и того же.
Спасибо.
Я просто сам сейчас это Фукса читаю, пытаюсь его добить до конца.
Well, let us proceed. Actually, another why стоп, не будем пока продолжать.
Это, наверное, идет запись. Вот
Да.
так просто делаем.
Okay. I'm sorry.
Let us proceed. Why this is useful? The matter is that not only in this situation, but in general situation, we can say what will be the product. And it is very nice that we can say in geometric terms what is the product of Poincare dual classes. To do this, let us discuss first the following important situation. Assume that, for vector bundles, we have an important operation of direct sum. Assume that we have two vector bundles over the same base. The first one with fibers of dimension n1, the second one with fibers of dimension n2. Then we can form their direct sum, whose fiber is just direct sum of these fibers over every point. Yes. So we have this projection with fiber of dimension n1 plus n2. Yes. And of course, we have here this projection and that projection, but of course we have got also these projections. Yes, we can consider this total space E as vector bundle over E1 with fiber Rn2, and we can consider it as, let us here introduce notation P1 and P2. Just I need some notation for that projections. So we have this situation. What can we say? I would like to say that we can write down the sum class for E from, if we know some classes for E1 and E2. Well, how do you think? What will be the answer? I would like assume that we know some class for E1 and some class for E2, and I would like to write down the sum class for.
Maybe it will be pullbacks, sum of pullbacks of tone classes for 1 and 2.
It cannot be sum. The matter is that some class for E1 product, of course. Yes, yes. This is a product of pullbacks. We have here in E1 we have some class for E1. It lives here in E1, and we would like to take its pullback over P1. Yes, and we need to multiply it by why this is true? First of all, look, some class must be represented by a form with compact vertical support. Well, but now we have two vertical directions. We have direction along E1 and direction along E2. So if we look along M, I will draw a picture where M is just a point. I look on my picture along M. Then say we have E1 in this direction, yes? And we have E2 in this direction. Well, then look, this some class phi E1, it lives on E1 and it has such compact support here. Yes? When we consider this, so it has its support in some neighborhood here. Well, when we consider this pullback, it has support in some strip like that. So it is compact in direction of E1, but not in direction of E2. Well, similarly for the second form, you have got a strip like that. And then the product is compact vertical in both directions. So this is well defined. Why? This is actually the Thom class. Actually, we had the following characterization of Thom class, that if we have a form with compact vertical support, which integrates to one along fibers, then this is a Thom class. If it, a closed form, yes, a closed form with compact vertical supports, if it integrates to one along fibers, then this is a Thom class. We have proved this. Look, our form is closed. It's a product of two forms. It has compact vertical support in our new bundle, and it integrates to one along fibers. Why? Well, the matter is that on each fiber we have the following standard situation. We have R and 2, R and 1, then well, times R and 2. We can not draw M as a point, but we can take here a point if we are in one fiber. And then we have got a form here, yes, which integrates to one. And we have a form here which integrates to one along E2. Well, and then their product integrates to one along Rn1 times Rn2. This is just well the standard formula like that. Where here x and y is not a single variable, but x is in one variables and y denotes in two variables. So we get just such very standard formula, and this guarantees us that this is actually a Thom class. And now what this gives to us in our situation. There is the following important notion of a transverse intersection of submanifolds. Assume that we are in the following situation. We have a manifold, and we have two submanifolds of it. R of dimension R small and S of dimension S small. By definition, R and S intersect transversely. Yes, we again in this situation it is always important. Also important that they are topologically closed, and we will always assume this. If the following is true, if for any point in the intersection, for any point in the intersection, what we can consider? We can consider a tangent space, the tangent space to R and the tangent space to S at this point. And the claim is that the sum of these two, both are subspaces of tangent space to M. we do not require that this sum is direct. For instance, if you consider two planes in usual free space, then they intersect transversely. We have two-dimensional tangent space here, two-dimensional tangent space here, and we get the whole tangent space. Well, if we consider two intersecting lines in free space, then the intersection is not transversal. We have the tangent space to one line, tangent space to another line, but the sum is not the whole tangent space to R3. So this is a definition. And this is a definition. And actually there is theorem which is also due to Tom, 1954. Theorem is that for any two submanifolds, one can consider an isotopy of one of them. One can make an isotopy so that one of them, so that they become transversal. To be more precise, for any R and S, what is an isotopy? Submanifolds in M. What is an isotopy? An isotopy is just a map from M times segment to M, such that any fiber of it, any level of it, such that H restricted to M times T is a diffeomorphism. And we start from the identity. So look, you start from identity, diffeomorphism of M onto itself, and you start changing this diffeomorphism, but so that it remains diffeomorphism at any moment of time. And you arrive to some different situation. So not to write this H restricted to M times T, we just write HT instead of it. So we can achieve that we can take such isotopy of the first submanifold so that it becomes transverse to S. This is theorem. I am not going to prove this theorem. It is not so hard, but it is somewhat cumbersome. A good exercise is to prove this theorem in situation when one of the two submanifolds has trivial normal bundle. In that case, this is just a good exercise on usage of Sartre lemma and something like that. So,
What lemma?
Sartre, lemma Sartre. So, exercise is prove this for say R with trivial normal bundle. And this case shows that it is very it gives us intuition that this must be true in general situation, but I'm not going to prove it in general situation. In the general situation, it is not an exercise; it is more complicated. But in this case of trivial normal bundle, this is more or less an exercise. Well, and actually it is very convenient. A huge part of mathematics says that let us put something in transverse position, and then it's very convenient to work with them. And well, now I would like to give another exercise, but this is actually an easy exercise on я потом забуду. Я хочу в листочке это включить. Просто, если не сложно, зафиксируйте, пожалуйста. Another exercise, it is actually not hard, that if R and S are in transverse position, if they intersect transversely, so if R and S intersect transversely, then the following holds. First of all, their intersection is again a smooth submanifold. Generally, if you have two smooth submanifolds, they can intersect rather, not in a good way, but if they intersect transversely, then the intersection is a smooth manifold. And we can say of which dimension. Of which dimension, it is very easy. Of course, we need to take sum of this dimension minus the dimension. Of dimension R plus S minus M. So codimensions at its codimension is sum of codimension of R and S. And besides, we can say what is the normal bundle of this intersection. The normal bundle of this intersection is the direct sum of the normal bundle of R restricted to the intersection plus the normal bundle of S restricted to this intersection. So the picture is like that. This is R. Oh, no. Yeah. This is R. This is S. We have transverse intersection, but we can have transverse intersection over some submanifold. Just in my picture, this submanifold is a point. I just cannot draw a picture. I can, but it will be harder. Okay, we have normal bundle to R, and we have normal bundle to S, and they intersect only by zero, and their sum is exactly the normal bundle to the intersection. Maybe a better picture is like that. Let this be R, this be S, and this segment be R plus S. Then you have one-dimensional normal bundle. This is to S, and that is to R. Yes. And their sum always used. So this is an exercise. And once we have this exercise, I'm sorry, I had here the formula for Thorne class. Thorne class for direct sum was obtained like that. And then, taken together this one and that one, look, we know that the planetary dual is the image of Thorne class of normal bundle. Normal bundle for the intersection is obtained as direct sum of normal bundles to R and S. But then corresponding thumb classes. And again, thumb classes for them are Poincare duals of R and S. Oh, I'm sorry. I forget to switch off the sign. So, altogether, this yields the following. And this is a very important consequence. This yields immediately the following corollary. Corollary is that if, again, all what I say is in the case of transverse intersection. And if R and S intersect transversely and all of them are oriented, M is oriented, R is oriented, and S is oriented, then the Poincare dual of this transverse intersection, yes, is the product of Poincare duals to R and S. This is just by this and this together immediately give this.
То есть ориентация на пересечение зависит от порядка
Yes, this is very important thing. The most unpleasant thing in the whole topology is size. Of course, we need to care here on orientation. Of course, product in one direction and with another direction is not the same. How we need to care on orientation? In fact, when we say that we have this isomorphism, here is the place where we need to care about orientations. If we have an orientation of R, then to this orientation corresponds the orientation of normal bundle. Yes? And to S, orientation of normal bundle here. And then R, okay, the intersection should be endowed with orientation which comes from these two orientations. Then this is true. Well, if the orientation is opposite, then of course you need to decide. Similarly, completely similarly, if one of the either R or S is compact, then we can replace the corresponding class with this compact version of class. And an important thing is that it is enough that one of them is compact, then the intersection is also compact. And the same is true. So if, say, R is compact, then this compact version of the intersection is this lives in compactly supported cohomology, this lives in usual cohomology, and multiplying compactly supported by usual general cohomology, we get into compactly supported cohomology. And again, the proof is exactly the same. So these are very important. This is a very important corollary. This is a very important corollary. And it allows us sometimes to compute products without any computation of differential forms at all, just by taking transverse intersection of the corresponding manifolds. And actually this is a very deep idea in topology, that product in cohomology is dual to transverse intersection of cycles. This is true not only for smooth cycles, but for non-smooth it is much harder to define what is a transverse intersection of cycles. One can do this, but this is harder, and we will not do this. But this situation, still the situation of smooth cycles is the most important, and it is very deep relationship between transverse intersection of cycles and multiplication of corresponding differential forms. And maybe the most important case here is when R plus S equals M. Then what can we say? If R plus S equals M, then the intersection of the intersection is a smooth manifold of dimension 0. So intersection is just finite. Assume that R, at least one of them is compact. Yes, then intersection is finitely many points. Well, and the situation is like that. Look, this is the situation of R plus M equals M. You have got R, and you have got S. They intersect transversely. Once R, S, and M are oriented, we have orientation of this space, of that space, and of that space. And we can ask whether they agree or not. So, these intersection points obtain signs. We can, for each intersection point, we can see whether this is positive orientation or negative. And look, around each of these points in M, we have such form, well, which integrates to 1. But forms corresponding to plus signs we need to take with plus sign, but forms corresponding to minus points we need to take with minus sign. Then if we integrate, we just get the number of positive points minus the number of negative points. And we arrive to the following conclusion, that if we integrate this form over M, then we just get the algebraic number of intersection points of R and S, where these points must be computed with signs. So this is a very important corollary, which allows us to write down some integrals immediately. So corollary is, again, corollary of that corollary is that if R plus S equals M, then if we would like to integrate over M this product, but I prefer to write down this. If we speak about forms, then it is better to write down this sign. If we speak about classes, then it is better not to write that. Doesn't matter. This is just the algebraic number of points in particular. This algebraic number is independent of the isotopy. When we do isotopy, of course, we do not change we do not change the dual homology class. So this algebraic number doesn't change. It's independent on how we make two submanifolds transverse to each other. This is very useful corollary, and it is often used to compute product of cohomology classes. Well, maybe that's more or less all for today. Is the part of lecture. to return to CPN. Well, why? Because actually this corollary gives us very important tool to compute powers of that form. So let us return to CPN, and I just recall what we made, what we already know. Yes. Well, CPN is a very important example, and it is indeed very convenient to work with it, and it is very important also. What we know, we more or less know the following. I forget what letter we have used to denote that to form. Just I forget about letter. Was it phi?
Maybe phi.
It is not so important. Well, we constructed two form on CPN, which is closed. Yes, and which is written very in precise way in, say, coordinates. I just would like to recall that we can write it down like that. In non-homogeneous coordinates, say very similar. Okay, here we have sum of lambda. This is lambda. This is lambda bar, and here we have maybe we wrote this formula in somewhat different ways, but okay, all of them are completely equivalent. So we have something like that. This is a great. Well, and we need here some normalization coefficient. Yes, and actually we have computed this coefficient from. We would like to have that integral of this phi over CP1, which is a two-dimensional sphere.
To be one.
To be one. And then the coefficient is I over 2 pi. So we have computed this, and we have written this formula maybe in somewhat different way, but more or less like that. Okay, so what we know? We know that such formula exists. It is like that. And well, and the next problem was we would like to obtain the following. We would like to say that, first of all, the question is, what is the integral of, okay, we can integrate phi over CP1, but we can take some power of phi. Say, we can take kth power of phi, and then it is natural to, inside CPN, we have CPK of all dimensions. So of course it is natural to integrate this over CPK. And we have a question, what is this? And the next question is that this guy is generated by the cohomology class of this form, and it's just the polynomial ring in this form. We more or less know this editively. Yes? As far as I remember, we also described, we also have discussed this. At least I gave you this as an exercise that using Meyer Vittoris, we may understand that the homology here are in even dimensions and zero odd dimensions. So if we understand that these are non-zeros, then we immediately obtain that result. But how to understand that this is non-zero?
Because phi is some class of normal bundle to CP n-1.
Yes. It comes from class. This was also a problem which I gave to you, and now we can in this notation we can say that phi is the Poincare dual of CP n-1 in CPN. And why this is true?
Because if we have CP n-1, it's tangent bundle in... Короче, если по-русски, вот у нас том класс, у него интеграл по слоям равен 1, вот, а когда у нас CP1 в CPN, и мы берем там нормальный слой, это как раз будет в маленькой окрестности кусочек CP1.
Well, I repeat what Alexei.
Yeah.
I repeat what Alexei said in English and in somewhat more convenient for me form. Look, if we have CPN, little CPN, and we have CP n-1 inside it, we can say that, for instance, this corresponds. CPN is the set of lines in Cn+1. Yes, and this Cpn minus 1 corresponds to some Cn inside of Cn+1, and there is a complementary C. We can always write down Cn+1 as Cn and C. Yes. One moment. No. I say that on purpose. We need to take not C. We can also say C2 here. This C2 and this Cn, we can achieve that they intersect transversely. Then we get here CP1 corresponding to this C2. For instance, let's be precise. Assume that here we have bases E0, En. We can take Cn, which corresponds to E1, En. And we can take C2 corresponding to E0, E1. Yes? Spanned by them. Then the intersection consists of a unique point. You have only one line, which lies both here and here. This intersection corresponds to the line spanned by E1. What can we say? that our form phi restricted to this CP1 integrates to 1. Yes? So this is, phi is a closed form which, being restricted to this CP1, integrates to 1. And we can consider similar CP1s over all points here. We can, okay, for each vector, we can consider this C2 not by spanned by E0 E1, but we can span it by E0 and arbitrary vector V in Cn. Then we get this CP1 with parameter V. And you get these fibers like CP1 V. And what we know? We know that our form phi, if we are restricted to each CP1, yes, then it integrates to 1 along it. Is it enough or not? It is not completely the same.
We can start with form which comes from Thom class into Bill neighborhood.
Yes.
And see that its integral over CP1 is 1.
Yes.
And therefore,
yeah. That's good. If we start from a priori, it could happen that this is not a good form. But the matter is that what helps us? What helps us is that we have only one cohomology two-dimensional class of CPN. So, indeed, you can start not from that phi, but you can start from Thom's form of CPN minus 1. Yes? You can consider normal bundle to CPN minus 1, and you can obtain Thom class of this normal bundle. It lives in two-dimensional cohomology with compact vertical support of this tubular neighborhood. Then we may come to cohomology of CPN, two-dimensional cohomology of CPN, and it is represented by a form whose support lies in a small neighborhood of CPN minus 1. And it integrates by 1 along every fiber of this normal bundle. But fiber of normal bundle is exactly this CP1, part of this CP1. And our form is 0 outside this tubular neighborhood. So our form integrates by 1 along any CP1. So we know that Thom's form integrates by 1 along these CP1s. Yes? So we know that this guy integrates by 1. But we also know that this guy integrates by 1. But using Meyer-Vittorius, we easily obtain that actually two-dimensional cohomology of CPN is only one-dimensional. So if they integrate by 1, both integrate by 1 along CP and CP1, then they must coincide. So for instance, we can obtain this like that. So we actually have this very important equality. That phi is equal to that form. Now how to compute the case?
No, we need to take n transversal CPN hyperplanes and show that their intersection number is precisely 1.
Yes, but that's more or less immediate.
Since they transverse.
No, yeah.
Yes, indeed. The matter is that, of course, this is true for any CPN minus 1 in Cpn minus 1 in Cpn corresponds to a subspace of dimension n here, to a hyperplane here. So, and this is true for any of them. And so we see that actually claim is that first we have already discussed that phi is the Poincare dual of Cpn minus 1 in Cpn, but the next step is that kth power of phi is the Poincare dual of Cpn minus k in Cpn. And the idea is exactly as follows: that that if we consider Cn plus 1 and we consider k hyperplanes, but k hyperplanes in general position, transverse to each other, so that they are given by linearly independent linear equations. Yes? K hyperplanes, and when we start intersecting transversely to itself, but to intersect we need to consider different Cpn minus. Then we get Cpn minus 2 and so on. And we arrive to a point. And so this example shows very well how intersection corresponds to multiplication. So the fact that Cpk and Cpn minus k intersect in a single point comes to the fact that integral is 1. Well, so we still have
20 minutes?
15 minutes, yeah. 20?
Yeah.
Oh, even. Well, then I tell you one another important thing. In this course, I have already said this, that in this course we often formulate, I often formulate theorems and say that they are proved by Mayer-Vitoris. And now I proceed doing this. I don't want to. There are two important theorems. First of them is the Kunin theorem. It says us how to compute the Dirac homology of the product of two manifolds if we know the Dirac homology of summons. The answer is as follows. If we would like to compute the Dirac homology of the products of two manifolds, then we need to write down as follows. We have tensor product the sum is over all pairs of k and l such that k plus l equals m. And the same for completely supported case. In both cases, we have an obvious map from right to the left. If you have got a form on M and a form on M. The map from right to left is just on the level of forms. If you have a K form on M and an L form on N, then you can get into K plus L form on the product just by taking, okay, if you have form phi here and form psi here, then you get into, you need to say that M times N has two projections, P1 to M and P2 to N, I2. And you can just do like that. Raise both forms to M times M and get a form of this. And the fact that this map induces an isomorphism in cohomology is proved just by Meyer-Vittorius. Alone, we just need to, again, this is true in general situation, but we will prove only for finite type. For finite type, we just decompose one of the manifolds, say M, into pieces and prove this by Meyer-Vittorius. Completely in a standard way, so I don't want to repeat it once more. And so in all situations like that, the only thing is to formulate correctly the statement. If you formulate it in a proper way, then the proof is just by direct diagram analysis. And there is another more less obvious and more interesting theorem, which is called the Reh-Hirsch theorem. The good question is, okay, this is for direct product, but instead of a direct product, we can consider a more complicated thing, namely a locally trivial bundle, a fiber bundle with whose not a vector bundle, but a fiber bundle whose fiber is also a manifold. So assume that we have this situation. We have bundle over some manifold M with fiber F, where M, F, and E are all smooth manifolds. This is just fiber bundle with fiber smooth manifold. And a natural question is how to compute cohomology of E starting from cohomology of M and F. Actually, this is a well-known algebraic topology problem, and usual solution of it is via theory of spectral sequences. We will not discuss spectral sequences. There is one situation where the answer can be given more or less explicitly, not to the very end. But there is one case when we do not need spectral sequences at all. What we assume? We assume that all manifolds are of finite types, M, F, and then E is automatically of finite type. So, of finite type. And also, we assume that we know a cohomology of F, and in particular, or well, assume that we have a basis cohomology of F. Just in cohomology of all dimensions. And sometimes it happens, it is not obligatory, it is just some assumption, but in several situations it is satisfied, and it is a very useful theorem. That assume that we can find cohomology classes on E with the following property, that their restriction to each fiber give basis in cohomology of F. So, more precise, so this is called Leray Hirsch theorem, and it is assumed that we have cohomology classes E1, En in cohomology, in the RAM cohomology of E. Star here means the direct sum of all N, so these are cohomology classes of different dimensions. Well, some of them are the same dimension, but generally of different dimensions. With the following property, such that if we restrict them for each fiber, we can have fibers over various points for each fiber. But actually, well, these restrictions form an additive basis, just as a vector space, of cohomology of F. An additive basis of F. Well, this is assumption. This is by no means true in general. For instance, I think you met such things as there is Hopf fibration, Hopf fiber bundle. S3 goes to S2 with fiber S1. Look, you cannot have cohomology of S3 which restricted to S1 gives a basis of cohomology. It is completely impossible. So this is an assumption. It is by no means true in general. Assume that we have such classes. Yes, and one comment about any fiber. Actually, if it is true for some fiber, then it is true for all fibers over the same connected component of M. Mm-hmm. Since the impedance of fibers are homotopy to each other. So actually, we can say for one fiber if M is connected. If M is connected, we just can say that for one fiber. If M is not connected, then we need to say that for any fiber. Okay. What can we say then? Then, look, an important thing that cohomology of E is always module over cohomology of M. If we would like to multiply a form on E by a form on M, we just need to raise this form on M and to multiply it by a form on E. So cohomology of, this is general fact, that cohomology of total space, of course, is always a module over cohomology of the base. But in this situation, the claim is that cohomology of E is a free module over cohomology of M with basis E1, En. So these classes E1, En form a basis of cohomology of the total space over cohomology of the base. So the claim is that this is a free I star of M module with basis E1, En. In other words, this means that we have such such isomorphism. And here is tensor product with space spanned by E1, En over R, but this is only isomorphism of graded vector spaces, not of algebras. This isomorphism, we have no good multiplication here. Multiplication, so this theorem doesn't give us a way to describe multiplication. And it is important that multiplication can be different. This theorem allows us to describe additive structure of homology of E and not multiplication. So, and important that this is isomorphism of graded vector spaces. That's the formulation. The proof. If M is Rn, if M is just vector space, then this is more or less trivial. We just have the isomorphism between homology here and here. Mm-hmm. Well, if M is with the homology here and here. If M is homotopy equivalent to a point, then this is trivial.
Расслоение тоже тривиально.
Separation, fiber bundle is trivial. This is just R, and our theorem more or less says that if E1 En is a basis, then it is a basis. So this is just tautology. And then just use Meyer-Vittoris. So this is an exercise, prove this by Meyer-Vittoris, but again this is completely extended. Prove this by Meyer-Vittoris. Sequence, but do I have 5 more minutes?
Yes.
Having in mind that this theorem, we need only 5 minutes to define Chern classes of vector bundles. Maybe I will be too quick now, but we will return. This is a very important point. We will return to it on the next lecture, but I would like to give it now. Look, assume that we have not that situation. We have now a vector bundle, but a complex vector bundle. Of dimension. I prefer to have a complex vector bundle. Well, with the dimension f over M. What can we do? We can consider an associated bundle, fiber bundle, with fiber. We can, over each point of M, we can consider the projectivization of the corresponding fiber. The set of lines in the corresponding fiber. Well, so, associated with this bundle, we have a fiber bundle which is called the projectivization of E, whose fiber is Cpn minus 1. Look, but here we have a tautological vector bundle over P of E. What is the point of P of E? A point of P of E is a line in one of the fibers here. Yes? You can put here this. So the point of P of E is a point here is, to be precise, it's a pair point X M and line A. This is line in the fiber of the initial bundle over X. Yes? I can put here, I can consider L over this point. By some reason, it is more convenient to consider here dual, to take the dual vector bundle. So instead of tautological, I take the dual of tautological. But this is technical thing. Dual of tautological, and we get some, let us denote it by gamma, some linear vector bundle of P of E. We have already defined Euler class, well, of linear vector, well, not necessarily of linear, but linear complex vector bundle is oriented real vector bundles dimension. So we have a Euler class of this gamma. Where it lives? It lives in two-dimensional cohomology of P of E. Yes? It lives in two-dimensional cohomology of the base of this bundle. Its base is P of E. So E of gamma lives in two-dimensional cohomology of P of E. What we get if we restrict this
CPN minus 1.
This class to CPN minus 1.
It would generate.
It would generate, it will generate, and good exercise that it will be exactly the class of this form. We will, now I give a scheme, but we will describe it in more detail next time. But exercise that if we restrict it to a fiber, to CPN minus 1, yes, then it is just, let us denote the class of this particular form by phi. Yes? This is just U. Well, what then we know? We know that, look, let us consider such classes. We consider classes here in P of P. We consider the following classes. 1, E of gamma, this Euler class. E of gamma squared. Once we have this class, we can consider it squared, etc. up to this is CPN minus 1, so I would like to write down here E of gamma to the power n minus 1. What can we say? We can say that we can take these classes for these E1, En. If we restrict them to an arbitrary fiber, then they form additive basis of cohomology of CPN minus 1. This is exactly what we have proved just now. That its power form basis. Okay, so applying this form, this theorem, we see the following. We see that cohomology of this P of E, yes, is a free H star of M module, H star of M module with basis 1, E of gamma, and so n on E of gamma to the power n minus 1. But what I said a very important thing. This is only isomorphism of created vector spaces. So we do not know how the multiplication looks like. But there is multiplication. So we can consider E of gamma to the next power, to the power n. There is no reason why it is 0. Its restriction to every fiber is 0. But there is no reason why it is 0 at all. But what we know that it can be expressed through these classes with coefficients in H star of n. Well, this means that now I would like to write down an arbitrary linear combination of these classes with coefficients from H star of n. What does it mean that it is coefficients from H star of n? It means that we have some cohomology classes on the base, which should be raised into P of R E and multiplied by these. According to some reasons, some signs here must be taken. This is just convention, we can take any. So we know that there is a linear combination like that. Some linear combination equals 0. Once we know that this is a free module with this basis, we know that any element, actually any element, but in particular this element, can be written in this form. For some C1, Cn in the cohomology of the base. And of course, by dimensional reasons, Ci is an element of cohomology of dimension 2i. Definition: these C1, Cn are called Chern classes of the bundle E. And look, the construction is functorial by our vector bundle. We just take vector bundle, do some constructions, and get them. There was no arbitrary choice. So the construction is completely functorial. Functorial, hence these Chern classes automatically satisfy the naturality, functoriality properties, and so on. But okay, this is a scheme, and we will describe. I'm very sorry, it was too long. We will describe it in more detail next time, but now let us stop.